My class before this is in friggin' Togo Salmon Hall, so it's a bit of a commute. All right. So how's everybody today?
Good.
Looking forward to the break?
Yes.
Sir, when is the midterm?
Okay. I'm thinking about pushing the midterm back, actually, to be honest. I think, I have not been getting through the lecture material as quickly as was done last year. For the test to be the same test, we're going to have to hold it like a week later or so. So I'm gonna ask me again after the break, basically, if that makes sense. Good. So we were talking about quicksort. Are we recording? Excellent. So quicksort then. I had given the demonstration using the numerical hexahedrons, and now our task remains to analyze quicksort to see why it's good, why it performs well. I received a question in the last class, which I'd like to address now, as the answer to that question has come to light in my researches. The question was, why would we use merge sort over quicksort if quicksort uses roughly the same idea and is overall better in terms of runtime? In some number of lectures, we're going to see that there's also a concept of sort stability. So if a sorting algorithm maintains the relative sortedness of items with the same value, right? So if you think about a series of flights that are all on days, right? If you maintain the orderedness of that flight, of those flights, with respect to each other, when you're sorting them by day, then it's what's called a stable sorting algorithm. Merge sort is a stable sorting algorithm, and quicksort is not. So quicksort will scramble the order of these items relative to each other, but merge sort will keep them in place relative to each other. So that's one situation where you would want to use merge sort over quicksort. So there we go. So, we had gone through this, we'd gone through the pivoting algorithm. Here's your Java implementation. I'd just like to quickly go through the partitioning algorithm again, because it's slightly obscure. So, I'll just do it once. With the partitioning algorithm, right, remember, you take, one won't be a very good one, so I'll just flip those. You take one item, which is the pivot, right? And you start up with a left and a right scan. First you scan from right to left, then you scan from right to left, from left to right. What you're scanning for are items which are not where they're supposed to be. So if the left-hand side is supposed to be, if this contains only items which are smaller than the pivot, any items bigger than the pivot, stop the scan, right? So scanning, 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 stop. Then you start from the other side, scanning for items which are smaller than the pivot, so you don't have to look very far. In this case, you then swap them, right? Then you resume the scan. Scanning, hit one, scanning, hit one, swap. Scanning, scanning, hit one here, scan there, swap. There we go. Scanning, scanning, partition. Right? Now, this is not guaranteed to be sorted. Oop. although it will be more sorted than it was before. It's at least sorted with respect to the partition. So that's why we have to recursively call the sorting algorithm on this guy, right? Everybody cool? Quick sort? Excellent. So, we've already discussed the partitioning algorithm. This is a trace of the partitioning algorithm as applied to, one of our traditional, quick sort example type things. So let's talk about this algorithm now. Where's my laser sword? Did I leave my laser sword behind?
On the chalkboard.
Oh, thank you. Excellent. So, the partitioning algorithm is not that hard once you understand it, but it's a little bit more. It's I'd say probably the most complicated procedure we've talked about so far in this class, right? Although I hope everybody, I hope it's not like, causing any aneurysms in the crowd. You shouldn't make jokes about brain aneurysms, they're very serious. Note to self. Anyway, so you might, like the partitioning, the scanning algorithm, you can think of an alternative to it if you pop these guys into auxiliary arrays in the same way that we were doing with merge sort, right? So if you kind of, declare two auxiliary arrays, and then you take the pivot and sort well, that's not going to be very good, is it? Take the pivot, right? And then, less, greater, less, and then you put them like that. You can sort of get the same idea, right? It turns out that this is much less efficient and basically puts quicksort on the same level as merge sort with respect to its runtime characteristics. So basically you're blowing out most of the advantage that you would be deriving by using quicksort over merge sort, right? So there you go. Shuffling is key for the performance guarantee. So basically, although quicksort performs very well on average, its worst case runtime is actually no better than selection sort, which is kind of funny, right? So basically, right, the question is, if you want to see what the worst case is for quicksort, the whole thing hinges on the fact that these two partitions are not necessarily of equal size. They're not only not necessarily of equal size, you may not have one or the other of them. In the case where you are sorting a array which is already sorted, for example, let's just take a quick one, right? Small one here. 5. Let's imagine that's our array and we're quick sorting it, right? If we select this as the pivot, right, then no scan, partition, take the pivot, scan, that's a partition, take the pivot, right? You're not actually dividing the array. So, in the case where quicksort has to sort something that's already sorted, it actually performs no better than some of our more basic sorting algorithms, right? So, this is the key, this is the whole point of the randomization, selecting a random key to get. I would say, personally, selecting a random pivot is a much better approach than actually performing a shuffle on this array, right? that's just a lot of swapping. It's going to take a lot more time than just deciding on like one random number, right? And then using that as an index for where you're going to pick up the pivot, right? So I would say that's probably an improvement. But so the reason that that improves things, right? If it's a random, if you are randomly selecting the pivot, then even if you are in the worst case scenario, it's highly, highly unlikely that you will randomly pick 1, 2, 3, 4, 5. And that unlikeliness increases as you increase the size of the thing you're randomly selecting, right? Make sense? So, like, it's a bit counterintuitive, right? Because, you know, in theory, we're trying to put things in order. Why would we need to introduce disorder to put things in order, right? But it turns out that, you know, what you're trying to do is you're trying to maximize the size, like this. You're trying to minimize the difference in the size of the partitions, right? Because perfect partitioning is dividing it perfectly in half each time, right? So the closer you get to that, the happier the algorithm is. Make sense? Question?
Would another approach be to calculate like the median element? Or?
Yes, actually, the question is how much time do you want to spend finding the median element, right? One of the big as we're going to see, actually, not on this slide, but on a slide coming up very shortly, one of the huge advantages of quicksort, not only like structurally, the size of the code that goes in the inner loop is very small relative to both merge sort and shell sort, right? So, in order to find the median, right, that's like, you know, at the very best, that's going to be linear, right? And like, I'm not actually sure what the complexity of finding the median is. It might even be n squared, right? So we don't want to introduce an algorithm that kills our runtime that way. Now, if you embedded things inside of the data structure that just automatically popped your median out, that would be a different question, right? And we'll talk about like something similar when we talk about heap sort, right? But yeah, but you're right. In theory, the median is the ideal pivot, right? Because the median is, of course, the number in the middle of the data structure, right? Or the number in the middle of that series of numbers. So, if you're always selecting the median as the pivot, then you're always producing the perfect binary tree, right? And always doing as near to a perfect partition as you can. The question is, how much time does it take to find the median? Make sense? Yeah. Question?
A question between the reckless pivot and the shuffling. So if for the worst case scenario, if this is already sorted, the reckless spot for pivot doesn't really still the whole selection will be still slow because that's the worst case scenario. The list already sorted. So whatever that you pick, it's still going to take project time to go through that whole sorting time. So I still think the shuffling is necessary because that's kind of make the list that is not sorted. Only
yeah, I see what you're saying. Yeah. It's about maximum tree depth, right? The reason that it's becoming an n squared algorithm, right? If you were to, I guess I've got red chalk today. If you were to if you were to produce the recursion tree for the worst case scenario for quicksort, it would look like this, right? If, let's say, I'm just going to put like the number of items in the node, right? So we start off with 10, right? then we have 9, then we have 8, all the way on down to 1, right? Where these guys, these smaller partitions don't even exist, right? So, you know, we don't even necessarily have to worry about them, right? So, the depth of that tree is going to be n, right? So, and, you know, you can make the argument, you know, the number of elements here is like n, n minus 1, n minus 2, etc., all the way on down, right? But sort of in the same way that like bubble sort, when you have a, you know, the triangle is still proportional to the area of the square, right? N squared over 2, that's still, both of these are still big O(n) squared, right? In that same way, despite the fact that this is a constantly decreasing series, it's still proportional to n, so in fact what you're ending up with is n squared, big O of n squared anyway, right? However, if you're picking a random pivot in the middle, like this structure is dependent on you always either picking from this side or that side, right? Let me add one more element here, right? So if you have an array, here I'll angle it towards you. So is that still good? Yeah, okay. So if you have an array which is already sorted and you're picking a random pivot, so right, this one, and that's the pivot, and we're scanning, right? So less than, there we go, there we go, there we go, right? So we partition, there we go, right? We've created 2 roughly equal partitions because I picked one that was already in the middle. So it's like the size of the partitions is actually related to like which position you pick randomly, right? So long as you're not picking out of the you know, ends too much, then your partitions are going to be reasonably equal, and you'll still have the nicely done binary tree that isn't just a line. Does that make sense? Cool. That was an excellent question. Thank you. Any other questions? Good. So, one other thing. With respect to the scanning algorithm itself, counterintuitively, it's actually best to stop when you hit an element identical to the pivot. You'd think that like stopping less and swapping less would produce better runtime, right? But as a matter of fact, this helps again to avoid the situation that we end up in here. Although I don't have a detailed analysis on that, that's just kind of a point on the slide that I'm taking as inherited wisdom. So, quicksort is considered the fastest sorting algorithm when the input is highly disordered. So quicksort performs well. In a lot of ways, it's kind of the inverse of insertion sort. Insertion sort performs well when the array is already ordered and poorly proportional to the disorder. Quicksort performs poorly when the data is ordered, but quite well when the data is highly disordered. So, yes. Half of all cases in quicksort execute very quickly. The inner loop of quicksort is very, very short. So, again, part of this shortness, like short relative to merge sort and, what's the other one? Shell sort, right? Both merge sort and shell sort require like a long series of copy operations in the inner loop before they start, you know, merging or performing insertion sort over that smaller array, right? In quicksort, this scanning procedure, only half of that scanning procedure actually requires looking things up in the array. Only half of it requires array access. In terms of like CPU memory usage itself, shall we say, you can store the pivot in register memory because it's not changing for the entire duration of the inner loop, right? So you're comparing to a fixed value that you don't have to look up. Whereas, if you're comparing merge sort and shell sort, for both of those, the two elements of the comparison both have to be looked up in the array, which, you know, takes more time because you have to fetch it from RAM, right? If we just bring in a few low-level details from oh, that's a grammatical mistake. It is difficult to have less going on in the inner loop, to be honest. Like, it is a very, very short inner loop. Both merge sort and shell sort move data within their inner loops. So, best worst cases. The best case comparison number of comparisons in the best case for a quicksort, sort of generally, n log n. And remember, do you remember what LG as a logarithm, what the base is on that? It's 2. Yes, thank you. So, best case, partitioning always creates subarrays of equal size. The recurrence relation is t at n is equal to 2t at n over 2 plus cn. Therefore, t at n is in omega n log n. Right? Worst case, number of comparisons is half n squared for the reasons that I already put on. Wow, that's really not visible. That's not very visible at all, is it? I'm going to see if I can find better chalk. Better chalk. I'm going to have to start bringing my own chalk, aren't I? Jeez. It's just like this place to not even have chalk. Jeez. There's a campaign against chalk. Anyway. So, in the worst case, partitioning always results in one partition of size 0 and all the rest of the elements in the other one. The recurrence relation is therefore t at n equals t minus 1 plus 0, t at 0 plus cn. Therefore, t at n is in big O n squared. This should indicate that, if this discussion has inserted just a seed of doubt in your brains about the whole concept of big O notation, then that's good. Because on paper, quicksort is a poorly performing algorithm if you're just looking at its worst case scenario, right? That being said, it is among the best sorting algorithms in terms of actual practical runtimes. Right? Make sense? In the average case, the expected number of comparisons is 1.39 n log n. That probably should be base 2 rather than base 10. Shoot. I'll look that up. But yeah. So although merge sort has the same running time, and quicksort does 39% more comparisons, quicksort is typically faster as it moves much less data. Again, it's the size of the inner loop that counts. So again, on paper, there's not much difference between merge sort and quicksort. You have to drill down into the constants to find which one is better than the other. Make sense? Any questions? So, here are a few practical improvements. All of the below suggestions are validated with refined mathematical models and experiments. The best choice of the pivot element is the median. Thank you very much. Even quicksort has too much overhead for tiny subarrays. Insertion sort outperforms quicksort on arrays of less than 15 elements. There is a non-recursive version using stacks, which always sorts the smaller half first. So if you're recursion phobic, then there is an iterative solution as well. I think there might be some recursion phobic people in the crowd. You should get over it. So, in summary, let's imagine we had a, various scenarios of number of numbers we're wanting to sort. A home computer, I don't know how old this is, but let's just assume that a home computer executes 10 to the 8 comparisons per second, and a supercomputer executes 10 to the 12 comparisons per second. You'll see that, let's just talk about million for a moment. On a home computer, insertion sort will take 2.8 hours. Merge sort will take 1 second. Quick sort will take 0.3 seconds. If you're trying to do the same thing, of course, on a supercomputer, only insertion sort over 1 billion items is taking any appreciable amount of time, although 1.6 weeks, I guess, would be quite an appreciable amount of time. So 1 billion items, right, on a home computer would take 317 years for insertion sort, 18 minutes on merge sort, and 6 minutes on quick sort. So you can see, in terms of practicality, quick sort is about 3 times faster than merge sort. Make sense? Any questions? All right, let's talk. Let's keep moving now. So, we're still talking about sorting algorithms. You thought we were done because the last topic said advanced sorting algorithms, and that implies, the termination of sorting algorithm. But no, we have one more sorting algorithm to talk about. We might call it a highly advanced sorting algorithm. So, we're going to talk about priority queues and heap sort. We are also going to learn what a binary heap is. That's not my computer making those sounds. Is that somebody else's computer making those wonky bug sounds?
It went longer through lectures.
Really?
Yeah. So, I don't know if it's something over there.
Maybe it's like this thing. I think it might be good. Yeah, I think it's this thing. Oh. Not a fan. Not about the picture though. Jeez. Anyway, so you know what? It's trying to do some goddamn Windows update thing. I think that's the problem. And that's, it's hooked into the AV system. Anyway. Priority queues. So, what is a priority queue? Well, it is a collection of objects which can be compared. It supports inserting an item and removing the largest or smallest item. We're going to talk about max priority queues. Again, it's this ascending versus descending thing with sorting. It doesn't matter which one we talk about, just flip the sign and flip the comparator and everything works the same way but in reverse, right? So, a priority queue is a data structure from which it is basically, you're always only interested in the maximum value in that data, in that collection, right? You want to optimize the data structure such that the maximum value can be easily and quickly picked out of it at any given time, right? So, in the same way that, okay, so up to now, when we've been talking about sorting algorithms, we've very much been talking about doing things over just regular arrays, right? Now, we're going to reintroduce some more advanced data structures in order to organize the data in a manner that's more similar to the union find algorithm that we covered a number of weeks ago, or 2 weeks ago, however long ago it was, right? So This is functions packaged with data which is organized. Right? So, if this is a trace of a priority queue, we have only two operations. Insert something into it and remove the largest thing. Right? So, insert E, insert X, insert A, remove the largest one, that's X, so we take it out, right? Etc., etc. Any questions about this? This shouldn't be too hard of a concept. Right? Cool. So, Jesus Christ. Applications of priority queues. Event-driven simulations, customers in a line, numerical computations, reducing round-off error, discrete optimization, scheduling, like, for example, when you have tasks being executed by a CPU, it's important to know which one of those tasks should be executed to maintain your computer's obligations to its programs, right? One of the better scheduling algorithms is known as earliest deadline first, right? That makes sense, right? I imagine a lot of you use the same algorithm to do your homework, right? So this algorithm would allow you, if you kept all of your tasks inside of this data structure, you can always very quickly pick out which task has the earliest deadline, because it would be a minimization, which of these is the minimum rather than which of these is the maximum, right? Make sense? Yeah, and then other things as well. Data compression, Huffman codes, graph searching, Dijkstra's algorithm, and Prim's algorithm. It's a Dutch name. It's pronounced Dijkstra. Not Dijkstra. So, here's your priority queue API. As expressed in Python. Of course, we are primarily interested in these three highlighted ones: insert, delete max, and is empty. But of course, it's reasonably easy to also obtain, just give me the max without removing it, and what is the size of this bloody thing, and the initializer given a set of keys, all of these types of things, right? We're not going to talk about the three grayed out ones, just the three ones that are in bold. Make sense? So, challenge. Implement all operations efficiently. This is generally the challenge of life. So, if we had two different data structures, right? We now know how to sort arrays, so we can talk about what runtime would be over sorted arrays. On an unordered array, we can insert things in constant time. We can delete, but to delete the maximum, we have to find the maximum, and that requires examination of every element. In an unordered array, we have the opposite problem. We always know what the maximum is because if you've sorted it in descending order, it's always element 1, right? So that's constant time. To insert something, though, it has to be inserted at its correct place in the data structure, which, of course, requires searching for its place in the data structure, which, if you're using something clever like binary search, then you could probably get that down to log n. But, in this example, we haven't talked about binary search yet, so let's just assume that we can do that in linear time. Our goal is to get both of these down to logarithmic time. Solution. Use a binary heap. So, binary heaps then. Very similar to the binary trees that we've talked about so far. The binary heap is in fact a binary tree which satisfies the binary heap property. So, further, it is a complete, so the binary heaps that we're going to be talking about for structural reasons related to how we represent them are always going to be complete. They're always going to be complete binary trees, right? So, no missing branches, right? So, in this case, our keys are in the nodes, and every parent's key is greater than or equal to the children's keys. This is the maximum heap property. So if you take a look at this example, again going by alphabetic ordering, T is greater than S and R is greater than O or A, S is greater than P or N, etc., etc. We are going to work hard to maintain the binary heap property despite our insertion and removal operations. It turns out that we can perform both of those things in logarithmic time because, of course, we're now dealing with a tree, right? So, first, let's talk a little bit about how we might implement this in an actual array. First of all, indices start at 1 rather than 0. You leave 0 blank for numerical reasons related to computation. It's not, basically the formula to calculate okay, all right, okay. In a binary heap, the positions of the children are calculated from the position of the parent, right? For any particular parent, for any two children, right, the positions of the two children in the array are 2k and 2k plus 1 if the parent's position is k. What that ends up with is a structure that looks like this one above. Essentially, these things are arranged by level, right? So the first element is the root of the heap. The next two elements are the children of the root node, right? The next four elements are the children of these guys, right? The next elements are the children of these guys. Does that make sense? So, if you continue that property on and you maintain the orderedness property that is the binary heap property we talked about on the previous slide, then congratulations, you have a binary heap expressed as an array. And of course, what's the advantage of doing things with arrays? Constant lookup time. Thank you. So, good. Any questions about that? Yeah.
Even though we're dealing with arrays over here, is it possible that we can do binary heap with a linked list as well?
Possible but not recommended. The constant lookup time is it strongly contributes to the runtime of the algorithm. So yeah, it's you could in theory you could use a linked list, but it would be less efficient. Make sense?
And one other question, for all the sorting algorithm we discussed, it can be done using both arrays and linked lists, or there are some that can only be done with arrays?
Anything you do with an array, you can also do with a linked list. It's just a matter of, if you walking the array to find the element you're looking for can contribute to a bad runtime. It depends on the structure, right? For example, if you were doing quicksort, a doubly linked list wouldn't be a bad way to go, because versus a singly linked list anyways, because in quicksort you're scanning both ways, right? If these nodes, those nodes ideally are connected both ways. But in a singly linked list, one of these scanning algorithms would have to scan from the one side every time it tries to move over, right? So that would be horribly inefficient, right? Make sense?
Yeah.
Cool. So, rather than simply sorting an array as quickly as possible, we now want to retain a sortedness property. With respect to insertion, we must add new nodes to the end of the heap in order to maintain it as a complete binary tree. We then, quote unquote, swim the node up through the heap until the sortedness property is reestablished. To remove the maximum node is more complicated than just removing the element at position 1. You must swap it with the end of the node and the node at the end of the array and then remove it. We then sync that node down, which is currently at root, until it finds its correct position inside the heap. So I'm going to do this. I'm going to do this with 2 items removed, and I'm not going to do it linearly. I'm going to do it as if it were, you know, a tree, because it's easier to visualize as a tree, right? Is it sufficiently clear what's going on here? Okay. I suppose I could bring like straws next time and lay the straws out. But if we're okay, then okay. I won't. Man, just arts and crafts time, eh? So, so first of all, this is like not at all arranged into a. So, just as a demonstration of swimming up, I'm going to do it to a few random nodes here since this is disordered, right? So you'll notice that these two are out of order, right? This guy in particular is out of order, so we swim him up, you know, swap these two guys, compare these guys, swim that guy up again, right? We'll notice, you know, this guy has to be sunk down. We can do that, you know, swim that up, or sink that down, right? Actually, there we go. Okay, so that's the binary heap properly established. Yes? Oh, wait, no, yeah, you're right. It's not quite established, is it? Right. No, we're doing a max priority queue, so we want the highest numbers at the top. Where's the 6? Yeah, oh, sorry. Yeah, look at the front of the die. That's the numbers I'm sorting on. Yeah, so this guy has to go, and this guy has to go, and that's good. Okay. All right. So, insertion. So let's say we have a number, right? 4. In order to maintain the complete binary tree, there's only one position at which it can be inserted, right? Right there, right? So we now examine it relative to its other nodes, and then swim it up if it's greater, right? In this particular case, it didn't it doesn't have to be. It's happy where it is, right? So let's do it again, and I'm going to pick one just so that it's a more interesting example. 6, all right? So that's connected to here, right? So it needs to be this violates the property, so we swap. Examine again. This violates the property, so we swap. Are these two all right? No, they're not. There we go. This violates the property as well, so we swap. This one ends up in the max position. right? So that's insertion. Let's talk about removal. We take this guy out, right? We actually, like, taking him out actually means swapping him into the lowest position, and then, like, in terms of the array, and then just ignoring the rest. Like, we reduce the size of the heap by 1. We put this guy at the end here. That's going to be, like, how we eventually result in a sorted heap. All right? But so we'll just leave this guy here now. Think of him as being disconnected from the tree. Right? So we've swapped this guy out. We need to sink this guy down in order to have him find his correct position. There we go. Right? So, heap sort then. Heap sort consists of continuous removal of the n of the maximum item while maintaining this binary heap property. So remove the max, swap it here, put it there, over there. This is a 2. Swap this then, swap that. There we go. There we go. Remove. Remove that, swap that here, put it over there. That's a 3. Swap here. Swap here. There we go. Remove. Swap it in there. Remove it there, right? 3, 3, 4, 4 there. There we go. That's good. Remove. Swap with this guy. Put it up there. That's a 1. Swap. Swap. Remove the max. Pop that guy up here. Swim it down. Or sink it down. Remove this guy. Right? This guy comes up in 2, 2, 2. There we go. There we go. Remove. Uh-oh. I think I must not have maintained my binary heap property, okay?
Yeah, you were before 3.
Yeah. It's easier, it's like, okay, I'm gonna stop the demonstration there because I made a mistake and that's horrible, but I just want to say one thing, right? From where I'm standing, I can't actually see the front of the dice unless I lean over them. So I'm actually a lot more like the computer than you might think, because I can only see dice that I ask to look at by moving my body.
Whoa.
Right?
It was all part of the, it was part of the plan.
It's all part of the plan.
It was
Yeah.
intended. It was intended.
I apologize for this this horrible mistake. I'll try it again next time, and maybe we'll get it done. We'll get it right that time. But you guys see that? This is called heap sort.
Wait, sir, but that's not very computer-like. You would never apologize.
Don't clap when I make a mistake. Eh?
Oh, I was gonna say that's not very computer-like. You would never apologize. The computer would just be like, take what you get.
Yeah, that's true. It's either take what you get or what's wrong with you.
Legit.
Yeah.
Yes.
All right. Thank you very much, guys.